let's get specific now and move on to the spatial weights, which, as we saw, was the formal way to express locational similarity. And before we get into the particulars, let's think a second why we actually need these. Because so far we haven't needed them. In geostatistics, we also had a notion of a covariogram, and we used distance. We didn't use these weird spatial weights. Now, why could we get away with using distance? Because we had this notion of a theoretical variogram. A theoretical variogram was a mathematical equation, like a spherical variogram, expressed in one or two parameters. And that mathematical equation was a function of distance. And so, as we saw last week, you plug in the distance, you get the covariance. Here, we don't have a continuous surface. We cannot treat our observations as sample points from a continuous surface. We have everything. We have the population. So how do we deal with it? And why is it a problem? Before we had the variogram cloud plot, all the pairwise interactions in the data set, well, up to a point, right? Now here, we're trying to model each of these pairwise interactions separately. And that's an unwinnable game. To put it more formally, there are n times n minus 1 over 2 different covariances, different spatial correlations in the data. And that's too much. There is no way we'll ever be able to estimate that with just n observations. So if you have 100 counties in North Carolina, there are something of the order of 10,000 spatial correlations in North Carolina between each possible pair of counties. So there's no way that 100 observations will allow you to estimate 10,000 parameters. It doesn't work that way. It works the other way around. So in order to get a handle on this, we have to impose structure, meaning we have to assume certain things. And anytime you do that, you can make a wrong assumption. Now, we did the same last week in the geostatistics. We assumed that the nature of the variogram was spherical or exponential. And then once we assumed that, we could get our sill and our range and our nugget, and with those in hand, we could estimate the covariances. Well, we'll do something similar here, but it won't be a function of distance. It'll be a function of neighbor structures. And we'll basically say, we'll define what the neighbors are. And the neighbors are those pairs where we can expect there to be correlation. And then the other ones, they don't have correlation. And that's how we will approach the problem as a first step. So there is no solution. Okay? It's an unwinnable game. You cannot estimate something, parameters, the number of which changes with the square of the number of observations when you only have n observations. That's an unwinnable game. So we have to do something, and what we're going to do is impose constraints or structure on the interaction by first of all saying only neighbors interact directly. That doesn't mean that others don't interact indirectly. That's a different story. We'll get to that later. But the direct interaction is between neighbors. And we'll say, well, we can't all be neighbors. We have to put in some limits. We have to put in some cutoffs where we say, okay, 5 miles is fine, but beyond that, you're not a neighbor anymore. We zero out. And that's a classic trick. When you have too many parameters, you just set them to 0 and forget about them, and then estimate what is left. And that's basically what we're going to do. By imposing this structure through this spatial weights trick, it's really a trick, we end up with just one parameter to estimate instead of n times n minus 1 over 2. Okay? And it's, in a sense, similar to what we did in geostatistics, where we said, Okay, let's simplify our life. It is a spherical variogram, spherical semi-variogram. By assuming that, we only have 3 parameters to estimate. We only had this range, cell, and nugget. And with that, we had all the information. Here, we'll go even a little further, and we, by zeroing out and putting this structure on the interaction, we'll end up with 1 parameter to estimate. And that then will give us, together with the weights, all the possible covariances. Just like in geostatistics, the parameters, together with the distance, gave us all the possible covariance. Here it's not the distance, here's the weights matrix. So the two always go together. And this is important also to remember later on when we actually compute things like Moran's I or Geary's C, which are spatial correlation statistics. They don't mean anything by themselves. They only mean something in connection with the weights that you use. Just like in the geostatistics, the variogram, the semi-variogram by itself, is not that useful. It becomes very useful when you assume a function, and then the function, the parameters with the distance give you the covariance. Here, the autocorrelation with the weights matrix gives you the covariance. So it's always together. So as a result, different weights, different autocorrelation. Just like last week, if we pick a different function, we get a different range. We go from spherical to exponential, the range changes. The nugget changes. Okay. So it'll be the same here. We'll change the weights, our autocorrelation coefficient will change. Now, how much? And does it become insignificant or stay significant? That's something we'll have to assess empirically. But the fact remains that never interpret an autocorrelation coefficient in isolation. It always needs to be looked at together with whatever you assumed for the weights matrix. So there is no such thing as the spatial autocorrelation coefficient. It doesn't exist. For a given weight structure, there is one. But for another weight structure, there's a different. Okay. So what we're going to do is just have this kind of running example where we have this spatial layout of 6 areas, and then we'll define neighbors between these areas. And running ahead, we'll define them as having a common boundary. So then, if we do that, we see that 1 is a neighbor to 2, 1 is also a neighbor to 4, and 1 is also a neighbor to 5. Right. And we can make this more abstract, and this is a connection to these social notions of matrix, because we can express this nice spatial layout as a network structure. And then each of our quote-unquote polygons become nodes in the system. So now node number one is connected to node number 2. The link in the network structure corresponds to the presence of a neighbor connection. So 1 and 2 in the previous slide had a common border. That common border becomes a link in the network structure. 1 and 4 have a link, 1 and 5 have a link. So you can think of this structure, you can think of this both ways. You know, we started with the map and ended up with the network structure. But you can do social network analysis, start with this, and then make the map. And ultimately what we see, it doesn't matter. These are all equivalent representations of the same structure. And what the spatial weights matrix is then is a mathematical representation of the same structure, mathematical in the form of a matrix, a square matrix. A square matrix of the dimensions of the data set. So if we have n observations, then for each of these n observations, we have n possible neighbors. So each observation becomes a row element in the matrix, let's say, location 1, then every other one, 1, 2, 3, up to n, is a possible neighbor of 1. Now, whether or not it is a neighbor, we'll quantify. And we'll say if it's not a neighbor, we'll set this to 0. And if it's not a neighbor, it's non-zero. Now, what it is, that depends. It could be 1 or it could be something else, as we'll see later. The important part is that it's non-zero. So formally then, we have a matrix, we'll call it W, which is n by n, and is positive. That's a convention, it's easier to do. And then we have a couple of things. For each location is in there as a row and as a column. For each row, the columns tell us what are the neighbors. The neighbors are those columns for which the weight is non-zero. If the weight is 0, they're not neighbors. Then there's one other thing. There is no self-neighbor relation. So you're not a neighbor to yourself. As a result, these elements here on the diagonal are all 0. Now that's a convention again. You could equally say, I am a self-neighbor. Then the diagonal elements would all be 1. Now, I don't care which one you take, as long as you are consistent when you derive this test statistic, estimate your models, and so on. And as it turns out, it's a lot easier to have these diagonals be 0 than to have them be 1. And so most of the work in this kind of spatial statistics, dealing with discrete spatial locations, has the 0 diagonal, has the no self-neighbor relation. Okay? But it's purely a convention, and every once in a while you may run into a paper that doesn't do this. And usually they have good reasons. It's based on theory or on the processes that they're studying. And as long as you don't make the simplifying assumption that the sum of the elements in the diagonal is 0, that's fine. Instead of being 0, it will be n. Right? You have n ones instead of n zeros. And as long as you carry that with you in all your calculations and derivations, we're fine. Where you go wrong is if you put in a 1 and then use the derivations that were made for the 0. Okay? Every once in a while that happens too, but you shouldn't do that. So for our purposes, we will just assume the diagonals are 0, no self-neighbors. That keeps it nice and simple. So then, for our particular example, this is what the weights matrix looks like if we just take the criterion of binary contiguity, meaning binary 1 or 0, and the criterion for neighbor is common border, which is called contiguity. So taking two contiguous entities, number 1 and number 2, number 1 and number 4, number 1 and number 5, those were the neighbors in our example. So now we have 3 representations of the structure of our data. We have our little map with the boundaries. We have our network structure, our graph with the nodes and the links, and we have our matrix with the zeros and the ones. And where we had a link between nodes, we have a 1 in the element of the corresponding element of the matrix. When we have no link, we have a 0. If there is a common boundary between the 2 polygons, we have a 1. If there isn't one, we have a 0. So these 3 are equivalent representations. Because statistics is about math, we'll be using the matrix in our expressions and derivations. But is just a way of formalizing the structure that we see in the network or the structure that we see on the map in terms of the common neighbors. As I said, the main thing is that when 2 locations are not neighbors, the weights are 0. When they are neighbors, they are not 0. But I said, well, what are they? And that's a big problem. They can be any of a number of different things. They can be based on geography. We already saw contiguity, but we can also build this weights based on distance bands, or more general complicated weights that are, say, a combination of the length of the common border and how far the centroids are apart between two polygons. We can have different graph-based weights, of which you have several examples in the readings. And then a whole can of worms, socioeconomic weights. In other words, just about anything you want to be a spatial weight can be a spatial weight. That doesn't mean you should use just about anything. The importance of the spatial weights, and the reason why the geographic ones are so popular, is that they are exogenous to the process. You don't determine the map. You don't determine the locations. And so there's a clear distinction between locational similarity and attribute similarity. You start to get into trouble when that distinction becomes vague, and then you get into circular reasoning. For example, if you say, well, I want to do a spatial autocorrelation, but I want to have economic weights based on unemployment rates. And I want to look at the spatial autocorrelation of unemployment. Then you're mixing everything together, because your so-called locational similarity is based on unemployment, and your so-called attribute similarity is also based on unemployment. Now, if you would say, well, I want to look at whether the religious, let's say we're in India and there's all these different complicated caste systems and religious combinations, we want to see if that has anything to do with labor market participation. And now we're defining a distance measure based on religion and caste systems. And the attribute similarity is based on, say, labor force participation. Then, with a lot of good explanations, you might be able to maintain that these two are separate. That's always the key. And it doesn't matter that much in the descriptive part, which is what we're doing here, but it matters a lot when you move on to the spatial regression and to the econometric part. These two have to be separate. So what you model in the attribute similarity has to be separate from what you model in the locational similarity. And that is why geographic weights are so easy, because you don't have to make that point. The location is exogenous to the attribute. Now, that doesn't mean that this is always the most meaningful thing to do. And definitely, if you're interested in social network analysis, socioeconomic weight structures are much more relevant in many cases than the purely naive common boundary from the geography. So even though that's the case, let's just spend a few minutes on the basics, the contiguity weights, the weights that are based on sharing a common boundary. I'd say of non-zero length. You may say, well, why do you say that? That has to do with GIS. We will, in practice, determine the common boundaries from the GIS, and depending on how precise the GIS is, some boundaries will be zero or some will not be zero. Also, what do we do with points? Common corners. Is that a non-zero boundary or is that a zero boundary? So given all this confusion, there are a number of three specific concepts that we can use to formalize contiguity. And they come out of similarity with the chess game. So they're called rook, bishop, and queen contiguity. And I'll start by showing you how they work on a regular lattice, which is pretty straightforward. And then I'll also show you how this extends, gets generalized into what we call irregular lattices, or just irregular polygon maps of counties, for example, or census tracts. So we start with a very simple layout of 9 cells on a 3 by 3 square grid. And we're going to focus on cell number 5 in the middle. Well, why? Because there are no boundary effects there. In all the other ones, we will have problems because C1, the neighbors that we see are 2, the things around 1 are 2, 5, and 4. But just like in the point pattern analysis, we don't know what's happening out here. So we have boundary effects. For all of these, in this very simple case, 8 of the 9 observations suffer from boundary effects. And only the one in the middle is free from boundary effects. So to keep things simple, we'll only look at the one in the middle. Now, in practice, we will not be working with 9 observations. Okay? So it's really a non-issue in that respect. But it's important to see the difference between the 3 definitions. And we start with the Rook one, which is the simplest one in the sense that it is the notion of a common border. So if we take that and we focus on the central cell number 5, the common borders are 2, 4, 6, and 8. They all have a common side. So using this Rook contiguity concept, we end up with 4 neighbors for our cell number 5. So 4 neighbors. Now let's change the definition and say, okay, neighbors are those cells that have a common corner, a common vertex. Okay? And that we call the Bishop pole. This is how it looks when you fill out the ones and the zeros. So it's, the one that we need to focus on is the one in the middle. That is 5. And you see 5 has 4 ones in it, 4 neighbors. And the other ones, none of them have 4 neighbors because they all suffer from edge effects. The ones at the corners have 2 neighbors, and the ones in the middle have 3 neighbors. So if you go back to the picture, you see 1, 3, 9, and 7 have the ones right above and the one right beside them as neighbors. There's only 2. Whereas these have 3 neighbors. The corner ones and the one just next to it. The one in the center is the only one that has 4 neighbors. But 4 is the rule. The others are the exceptions. These are edge, as we call them, edge effects. So the other thing to notice about this weights matrix, and this is very typical of regular lattice structures, grid cell structures, is this band structure of the ones. You see these ones, they kind of follow bands parallel to the diagonal. That is very typical of contiguity weights in regular grid structures. Okay, now let's move to our corners and our nice picture where we have, again, 4 neighbors, but they're not the same. So here, we have to start to be careful when we talk about the similarity of the values in a location with its neighbors, depending on whether we take Rook or Bishop. These are, in each case, 4 neighbors, but they're not the same 4. They're different 4. Okay, so the definition of the weights changes the notion of what locations are neighbors. But again, for the Bishop contiguity, we have 4 neighbors. Now, I should say Bishop contiguity is not used much. It's only used in those instances where you can reasonably claim that all the interaction goes through the corners, and there is no interaction through the cells. Now, there may be, situations where that's the case, but I haven't seen very many. Then before we go to the next one, this is what it looks like. Now, we have this kind of weird shape. You see this kind of patterning in here. Again, the one we need to focus on is the middle one, with 4 ones, and the rest are zeros. All the other ones suffer from edge effects. Now, the edge effects are a little different. If we go back, and say the upper left-hand corner, how many common corners does this have with another cell? Just one. So these four corner cells each only have one neighbor. Then the ones in the middle, they have two neighbors. So when we look at the weights matrix, we see that there's two here, but one here, one there, one here, one there, and they're all the same. Because their neighbor is 5. Is the central grid cell is the one that touches the corners of the ones in the corners of the grid. So the column that corresponds to that cell, the 5th column, has 1s in it for the 4 rows that correspond to the corner cells. Right here. So that's how you have to look at this matrix. So each observation is both a row and a column. So then, as I said, when you put the two together, you have queen contiguity. The queen can move up and down and sideways as well as diagonal. And then, now it's different. There's no longer 4 neighbors, but we have 8 neighbors. This case is a little extreme. They're all neighbors because we only have such a small grid cell. And we see that in the weights as well. For 5, we see all ones except the self neighbor. And then the others demonstrate a combination of these edge effects that we see for the rook and the queen. So, in a nutshell, on regular grids, the two that are used are either rook, common side, or queen, which combines the side and the corner. The difference between the two is that queen has twice as many neighbors as rook. Rook you have 4, queen you have 8.
Do you choose just based on your study, which
That's the million-dollar question. How do you choose the weights? And we'll talk a little more about that in the lab as well. There is no rule to choose the weights. Here, we're concerned with rejecting the null hypothesis. So we want to use weights that give us power in rejecting the null hypothesis. So we want to have weights that are able to pick up slight differences from the null, which is spatial randomness. So, as it turns out, it's a good rule of thumb to have fewer neighbors rather than more neighbors in a test for spatial randomness. So in that sense, everything else being the same, the rook would tend to be more powerful than the queen. Because, I mean, one intuition is that when you have more neighbors, there's more averaging going on. When you have fewer neighbors, there's less averaging going on. More averaging is smoother, is less variance, is less information. That's one way to think about it. But the important point that you raise is that this is a very difficult question. So my rule of thumb is that for exploratory analysis, rejecting the null, it doesn't matter that much. Because basically what you're interested in is finding evidence that there is no spatial randomness. So from my point of view, anything that gives you that evidence is good. Now, it gets different when you get into the model, because the modeling is an attempt to model the pattern of values that you observe. And so then you have to think twice, what is a meaningful neighbor structure that I put into my model? Do I just put in common boundary because it's easy to do, or do I take the queen because it's also still easy to do, or do I think up some highly convoluted socioeconomic weights matrix because that's theoretically more attractive? That becomes the real question then. And in the practical way to choose, if you wish, is to go to a criterion in some kind of objective function, for example, the fit. And so you pick the weights matrix that gives you the model with the best fit. That leaves aside how you measure fit, but we won't get to that. And all I can tell you is not that simple. But conceptually, that's a way to pick a weights matrix in a modeling context. You pick the one that gives you the best fit. Okay. In a testing context, we're concerned with power. Power has to do with the probability of rejecting the null when in fact it is false. That's the thing you want to do. You don't want to be wrong. So if the null is false, you want to reject it. And that's the power of a test. A good test is a test that always rejects the null when it's wrong. Now, no test is perfect. And because it's, there's randomness, it's a sample, there's randomness in the data, and so on, right? But basically, that's the idea. So we want to get a weights matrix that gives us an indication that something is not right with this data in the sense of it's not spatially random. So then the extension of this notion of rook and queen to irregular data follows in a pretty straightforward way. Rook is common border, so this yellow county shares about border 39, shares about border with 19 and 15, which would be the rook neighbors. Now if we also take into account the corners, then 67 gets in business as well, and that becomes a queen neighbor of 39. So in irregular situations, it really depends on the spatial layout of your units, whether there is a difference or a big difference between the rook and the queen criterion. And for example, when you have grid-like counties, like you do in Iowa and in Colorado, where it's basically square counties, then you will have a difference between the rook and the queen, similar to the difference we had for the regular grid, where rook has 4 neighbors, queen has 8, twice as many. Right? But if you have really irregular, these are counties in West Virginia, you see there aren't very many cases. I had to look very hard to find one like this, where there was a common corner but no common border, edge, if you wish. And again, this is where I have to point to the dangers of the GIS. It's really up to the precision of the GIS whether this is in fact a point or a very tiny little short line. If it is a short line, then rook will pick it up. If it is a point, rook will not. Queen will pick up both. So my preference is to avoid these kind of GIS-specific things, is just use queen. And when you have, how often is it truly just a single point? And what does that really mean? Is that really how the interaction happens through the single point? So my preference is to use queen as a criterion for irregular, highly irregular lattices, but to watch out for strong differences between the two. As I said, like Iowa and Colorado, where you have a lot of square counties, then there could be a major difference between using the rook versus the queen. But if it's like this, it's not going to be that big a difference. And in the lab, we'll see ways in which we can quantify the characteristics of the weights, which gives us some clue as to whether we might be running into problems or not. But I didn't want to spend a lecture on going over that. We'll cover that in the lab on Thursday. So this is where we are. We've kind of set the stage. You know the framework. We're looking at spatial autocorrelation. The null is, as before, spatial randomness. The alternatives are positive and negative spatial autocorrelation. The spatial autocorrelation test is something that combines a measure of attribute or value similarity and a measure of locational similarity. And to do the latter, we need these spatial weights. Then next week, we'll see specific test statistics.